Calorimetry is a technique for measuring the specific heat of a substance that you don't already know the specific heat of. It relies on the fact that the specific heat of water is known. So the way that calorimetry works is you start out with a container of water, and the container of water has a thermometer in it to measure the water's temperature. So you start out with the water being at a cooler temperature, some temperature of the water initial. Then you take a substance that you want to measure the specific heat of. Usually you start out with that substance in an oven. And so you raise it to a very high temperature, and you know the temperature of the substance because you know the temperature of the oven. And so you have a substance with an unknown specific heat at some temperature of the substance initial, and you put that into the water. You allow the substance and the water to exchange heat and the system to come to equilibrium. Then you can read the final temperature of both the substance and the water and use that final temperature, and specifically you use the final temperature exchange of the water to know how much heat left the material, and therefore you can measure the specific heat of that unknown substance. So if the temperature of the substance initially is greater than the temperature of the water initially, because say you put your substance in an oven to raise it to a higher temperature before it entered the water, then Q for the water will be positive. Heat is flowing out of the substance into the water. Q for the substance will be negative because heat is leaving the substance. But the two heat exchanges should sum to zero. The amount of heat that flows out of the substance is equivalent to the amount that flows into the water. And so if we know that the sum of those two heat exchanges is zero, we can write down for each material what that heat exchange is. So Q for the water would be MC for the water times the change in temperature, the final temperature minus the initial temperature for the water, plus the mass of the substance times its unknown specific heat times the final temperature minus the initial temperature of the substance. And then you can solve for the unknown specific heat of the substance. You'll notice in this equation that both of the final temperatures are the same, and that's because the entire system comes to the same final equilibrium temperature. Now, if you have multiple objects in thermal contact, maybe more than just two, for any isolated system, the sum of the heat exchanges will be equal to zero. So in the case we previously looked at, the heat exchange of the water plus the substance was equal to zero. And this is because if you have an isolated system, heat can just be exchanged between the pieces of that system. And if heat flows out of one thing, it flows into another. Now let's say we dropped a cold nail in as well to this system, then we would have to worry about the heat exchange for the water, the mystery substance, and the nail. But still we would know that since it's an isolated system, that all three heat exchanges would sum to zero. So let's look at an example problem where we use this strategy of summing the heats and setting them equal to zero. So in this example, we want to find the final equilibrium temperature when 10 grams of milk at 10 degrees Celsius is added to 160 grams of hot chocolate, which is at 90 degrees Celsius. And we should assume that the specific heat of the hot chocolate and the milk are the same as the specific heat of water. So what we know about this problem, since we have multiple things in contact exchanging heat with each other, is that the sum of those heat exchanges is going to be equal to zero. Here we have three materials that are coming into contact, or we have two materials that are coming into contact, and those are the milk and the hot chocolate. So we can say that the heat exchange for the milk plus the heat exchange for the chocolate sums to zero. And then we can be more specific about what these Q's are. So we would have that the mass of the milk plus the specific heat of the milk, which we're told is the same as the specific heat of water, times the final temperature minus the initial temperature of the milk, plus the mass of the hot chocolate plus times its specific heat, but we're also told that the specific heat of the hot chocolate is the same as water, times the final temperature minus the initial temperature of the hot chocolate. All of that sums to 0. And the thing that we're looking for is that final equilibrium temperature, which we see appears here and here. And we use the same symbol for the two different materials because they come to thermal equilibrium, so they come to the same final temperature. So if we know that we are solving for this final temperature, what we need to do first is multiply out over the parentheses so we can gather together the terms that have this final temperature. But before we do that, I think I can see a way to simplify this equation. And that is, since I have the specific heat of water both here and here multiplying each of these two terms, I can divide every term in my equation by the specific heat of water. So if I do that, it will cancel out here. It will also cancel out here. And then I divide 0 by the specific heat of water as well, which still gives me 0. So after doing that simplification, next I'll want to multiply these masses out over the parentheses. So I would get the mass of the milk times T final minus the mass of the milk times the initial temperature of the milk plus the mass of the hot chocolate times T final minus the mass of the chocolate times T initial for the chocolate sums to 0. So next I'll move the terms that don't have T final in them to the other side of the equation. So I have mass of the milk T final plus mass of the chocolate T final is equal to mass of the milk T milk initial plus mass of the chocolate T chocolate initial. Then I'll factor out a T final from these two terms. So T final times mass of the milk plus mass of the chocolate is equal to, still everything on this side, mass of the milk T milk initial plus mass of the chocolate T chocolate initial. And then I can divide both sides by this sum of the two masses. So T final is going to be equal to mass of the milk T milk initial plus mass of the chocolate T chocolate initial divided by the mass of the milk plus the mass of the hot chocolate. All right, so then I'm ready to plug in some numbers. And the mass of the milk, so the mass of the milk is 10 grams, which is equivalent to 0.01 kilograms. The initial temperature of the milk is 10 degrees Celsius, plus the mass of the hot chocolate was 0.160 kilograms, and then the initial temperature of the hot chocolate is 90 degrees Celsius, and then I need to divide all of that by the sum of those two masses, so 0.01 kilograms plus 0.160 kilograms. So then if I do that calculation, I get a final temperature of 85.3 degrees Celsius. So that would be the final temperature of the hot chocolate once the system has come to equilibrium. So next let's look at this question. A cold penny and a hot nail are dropped into an insulated container of water. If 10 joules of heat flows into the penny and 5 joules of heat flows out of the nail, what would be Q for the water?